Is that working now? Is it working now? That's right up loud. Or maybe that one as well, yeah. What about now? Weird. Okay. So this is rather similar to undergraduate lectures where it's always difficult to get people to move in somewhere towards the middle. They tend to like to sit around here. So my name's Douglas North, and as Deputy Dean, in the absence of the real Dean, who should be on the plane to Australia at the moment, it's my pleasure to welcome you to the 2019 Gibbons Lecture Series for this year. I believe I am using the microphone. It's turned up.
IT people.
It's turned up as loud as I can make it go. All right, so is that any better? We're on maximum. I think you're just getting deaf to it. Okay. The Gibbons Lectures are an annual series. The Gibbons Lecture Series is an annual series of talks that's hosted by the department. I should now say, of course, the School of Computer Science, so congratulations to you all for that. In association with ITPNZ, the Auckland ICT Graduate School, and as I understand it now, but also by Dr. Beryl Plummer, who's helping to support these events. The aim of each lecture, as I understand it, is to describe cutting-edge research in a particular area to a non-specialist but technically sophisticated audience, both within and outside the university. So I'm hoping that that's me. I come from psychology, and I understand some things, but some of the words in the abstract from Michael here was so difficult that I thought I'd better write it all down. The Gibbons Lectures are named in memory of Peter Gibbons, who was a former head of the Computer Science Department, of course, as you all well know. I didn't know Peter very well myself, being from psychology, but I do recall working with him on enrolment matters in the late 1980s and early 1990s. And I remember him as one of the most courteous, gracious, fundamentally decent people in the university, so I hope we all remember him as happily as I do. The theme for this year's lectures is quantum computing, and this evening's speaker is Dr. Michael Dinneen. It's particularly appropriate for Michael to be speaking in this series because one of the first things that he did in his time here was to teach several classes on algorithms shared with Peter Gibbons. So that's nice that should work out. Michael's early career, I'm reading this out, included work on grand challenge combinatorial search and optimisation problems at Los Alamos before receiving his PhD from the University of Victoria in British Columbia in 1996. And he joined us as a lecturer the same year. I understand that his main interests are in Idaho potatoes, Washington apples, and New Mexico green chilies. But apart from these things, he specialises in algorithms and graph theory, unconventional models of computing like adiabatic quantum computing, which I hope we're going to hear what that is tonight, and membrane computing, and he's written more than 100 papers on these topics. Michael will explain tonight what quantum computing is and how it differs from traditional digital classical computing, focusing on the school's research using a D-Wave 2X model at the USC-Lockheed Martin Quantum Computing Centre. Michael, the floor is yours.
Thank you very much. Okay, welcome. So hopefully the sound is okay still? Okay. So briefly the first thing is I want to mention that this talk is in memory of both Peter Gibbons and Bob Dorn, who actually organized the last 10 years of the Gibbons series, and unfortunately he passed away recently too. Okay. As mentioned, I was first hired, I remember the job interview for here was Peter Gibbons was one on the hiring committee that I did, so I was working in his area of graph algorithm, or that's what I do, but he was doing general combinatorial problems. I got hired, and Bob Dorn was the first head of department when I was hired. I remember him picking me up from the airport when I first arrived. Okay, so, as mentioned, I will try to start with some very simple, non-mathematical explanations what actually is quantum computing compared to with the standard digital programming that everybody does. I know it's a little bit complicated task, but at least I want to mention what it's all about and why people are so keen on working on that area now. Okay, so what is quantum computing? Originally, the first person who proposed it was Richard Feynman. He's a physicist. I'm not a physicist. I know very little of actually the physics. I'm a computer scientist, but I know how to exploit the property of quantum physics to actually do computations. And this is what a lot of applied computer science will probably do. So basically, even originating, I think this is 1981, Feynman had some problems that you wanted to simulate nature, basically. And basically, the only way you can do it, he proposed, is you need actually a quantum mechanism to do the simulations. Okay, so that's one branch of quantum computing that was motivated. So I put a sign as the original. So, and the first computers that are actually quantum was unfortunately way after he's passed away. But he was the originator thinking of quantum, of the need for quantum-based computing systems. Okay. Currently today, I just mentioned there's a lot of big players and companies that are actually getting into quantum computing. I just mentioned a few here. And sort of the states of how the progress is, how many actually, we have information for quantum computers we call a qubit, which I'll try to explain in a moment. So IBM, Google, Eon, they have various machines. There's actually different types of processes or motivations for quantum computers. So there's like parallel models. One, the more original ones from like MIT, all the theoreticians wanted something to simulate similar classical digital computers with circuits, and that's the quantum gate model. And several players are producing computers with that model. More recently, and actually the first commercially available computers are by other players, which are basically what we call the adiabatic annealing type quantum computer. And most of my talk today will be focused on that because that's what I'm using for some of our computations. Okay. And of course, they've sold them again to all the big players. And even governments are interested in quantum computers too. I think the next talk will be about cryptography and the need, so that some of the interests want to make sure your baking is safe. So you need quantum algorithms or make your encryption and so forth safe from quantum algorithms. There's other physicists, there's other models like quantum walks, where it's basically a generalization of random walk algorithm, discrete version, which they generalize to a quantum pass and a walk. So there's, I mentioned that as a weak third type model of quantum computer, which will come back. Okay, and more recently, which you've turned, big companies are actually building what we call these quantum simulators, where they're sort of discrete digital type hardware, but the model is, in the specification of your algorithms or whatever, actually inspired by the more expensive real quantum computers. So people can get these quantum simulators, Fujitsu and Hitachi, which are using some hardware that are customized, that are trying to mimic the actual quantum computers. They're not really a quantum computer, but they're trying to act. So you can debug your programs or whatever that you do on a less expensive machine, and then pay, hopefully, for more expensive. If you have say $10 million of spare cash, you can buy one of a real quantum computer from D-Wave or whatever. Okay, so this slide is basically just a name drop of all, to say that all the big companies are many more than listed here are actually interested in these. And I'll come to some applications in a moment later. Okay, just to add some more history, I want to give a little bit of pictures of actually the history of computers from the old days to the new days. So this is just a generic photo I got from the internet. And one thing to observe, most of the old mainframe computers fill the room. And another thing to notice, most of the old machines have little switches or things that you actually interact, like toggling states on the console or whatever. and also lots of wires, right, a mess. Okay, so 20 years in the further down the history line, this was actually one of the first computers in the 1980s, which was a Cray supercomputer, similar big size machine. And you can see this was a sort of a computer where inside of it, the guts of it is basically a rats of wires all messed up. You can sort of see the wires in the middle here. And they had outside, it's actually a fashion design, you actually could sit on it, but the functionality in the seat was power supply and cooling equipment that you can run in there. So this is one of the first computers the supercomputers I was using in the 1980s when I was at Los Alamos. They had one of these. Now they're all in museums, these computers. And the power of those computers now are less than probably even some of the cell phones. But they were big and bulky. But at this stage, notice they've dropped, there's no actual physical switches from the previous generation. You actually still communicated from an external terminal, and then the processing power was inside those. Okay. Moving on to now what actual quantum computers look like. So I got two examples here. One is the D-Wave. They're, again, big machines that fill in a server room. Instead of wires mixed up, it's actually a big refrigerator, a freezer. So they have a big freezer, and then you're supposed to shield from the environment. You're not, for quantum computing, you're not allowed to have vibrations or anything that will disrupt the computation. Okay, so this is the model that D-Wave is advertising on their site. A big, huge one. And inside, they basically have a little cooling mechanism that goes down, but the actual processing, or the qubits, are at the very tip of it. So that's what's inside one of those machines, the D-Wave machine. Call it enclosure. IBM, similar big structures. They have their quantum computer like this. It's a big casing mechanism. I guess their model is they're hosting them from the ceiling so they don't vibrate on the floor from people walking around on the floor. And one thing I noticed from these promotional photos, both of them have two of them. Because if you're going to sell a product, you have to convince the public you have at least two models, or at least two in existence, not just one computer that you can sell. Okay, and again, the inside photo of the IBM computer is very similar type structure. It looks slightly different, fatter, but it's basically, they have a mechanism to go down to cool the mechanism, and then the processing CPU is at the very bottom of the quantum structure. Okay, so that's just, it's nice to see what they physically exist and what they look like, okay? From the outside, they're not different, but the programming mechanism is now everything in the cloud. You communicate, so we can run our programs from the California system remotely from Auckland type thing. Okay, so now what I want to do is, why are they different from regular computers in terms of, well, basically we want to exploit the properties of quantum physics. And the things that you may have heard of are basically these three things that we can add in addition to the current digital computational process. One is superposition. Instead of having a single bit in one state, 1 and 0, we can have what we call a qubit will be in multiple states at the same time. So the computation will progress forward, and at the very end, only at the very end when we try to extract or read the results of the computation, well, we'll know the final computational result. Okay, so that's one property, superposition of states. Another property is entanglement. You can have two particles that you want to be entangled in the same spin. For example, I use a spin if they're both up or both down. Or you can entangle two particles that are opposite. Okay, there's two ways to pair up or entangle two objects. Okay, so you can, sometimes you need to do distributed. We'll see examples of how we entangle qubits to do the computation to get our results in a minute. And the last thing is maybe more related to the annealing, quantum annealing example that we do is tunneling. In standard computational process, if you're doing an optimization problem, you're like searching for a minimum or maximum of a landscape. Most of the time you have to climb or go up and down hills with the original. In the quantum world, there's something called quantum tunneling, and actually can go to the minimum state without having to go over heels or down the values. Okay, and this is the third feature that we want to exploit in our computational project. Okay, I'm going to first talk about superposition. You may have heard of somebody, Schrodinger's cat experiment. Okay, so this is a classic physics experiment where you put a cat in a box, you have a little radiation thing that triggers poison or something that will kill the cat. So the radioactive device has a half-life, but you don't know what it is or when it will go off. Okay, so you put the cat in the box with the radioactive device that will trigger the poison. You wait 10 minutes or whatever, a half hour or whatever. You want to know, you don't know if the cat is killed or not killed, alive or dead. So the computational process that we're going to do for computers is going to be the same thing. We have an object, a piece of information. We don't know if it's in the up or down position or 0 or 1 position, the state. But we will proceed, and only at the very end, when we look in the box, we'll decide whether the computational result. So traditional programming, when you learned your year 1 programming class, you usually had statements, is variable x equals 5, conditionally do something, whatever. So in quantum computing, we're not allowed those basic primitive if-then-else statements, because you're not allowed to look at the values of your variables or bits until the end of the computation. Okay, so that's a little different from the traditional digital programming that we're all learning. So in terms of quantum computing, when they become more reliable, we'll have to have a new skill set of how to program these computers. Okay, so one of them is we'll have to exploit superposition of bits, assume that the bits are in multiple states. Okay, and in a couple slides I'll show why that was useful. Okay, it's basically going to allow us to do highly parallel computations with many things in single steps. Okay, so a visual picture of what a qubit is. So a regular bit, that's the foundation of information of a computer that were built with relays, circuits, test tubes, you know, the history of building, but they basically all had 2 states, either yes or no. So if it's, you can have a voltage, electrical voltage, to say if it's above a certain level, it's a 1. So, but it's a discrete type mechanism. Okay, so I brought, here's a bit. That's 0 state, 1 state. But it's basically, you don't have a mixture of both with this sort of device. It's basically the trigger mechanism says it's either 0 or 1. Okay, a qubit, you can, this block sphere type visualization is sort of a good one to get the picture of a qubit. It's basically, you can view a qubit as a sphere, and any point on the surface is actually the value of the qubit. So there's basically an infinite number of states for 1 qubit. It's basically wherever they're pointing. So if it's a sphere of unit 1, you can be pointing anywhere. And the probability, if you read it, actually do the discrete reading, the Schrodinger's cat experiment, it will then collapse to either 1 or 0. But during the computation, you don't know where it is. It's just, you can think of it as pointing somewhere on the sphere, the actual state of the thing, or simultaneously at many positions with different probabilities. Okay? So that's, if you hear the jargon qubit, you can, humans can visualize a qubit as a sphere, and some point on the sphere is actual state of the qubit. Okay, so here's another patch. The state, so as I illustrated, a classical bit is either on or off. Okay, if you read papers on quantum computing or quantum physics, they actually have their special notation for 1 and 0. They have this bracket notation. So if you just see stuff which is like a vertical line, 0, an angle bracket, or 1. So that represents sort of spin up or down. That's the reading state. But the actual state of the object, you can have complex numbers and combine 2 states up and down into a mixture of states. So that will be the actual state of the qubit. Okay. And you have probabilities. So for different values of C1 and C2, the sum of the square values as 1 will be the point on the unit square, or the sphere. Okay. So we can view qubits, I guess human realization is, this is a nice way to view a qubit, as just a point on a sphere. Okay, and then we'll have probability. So the default one, if it's pointing here, the probability when you read it will either be 0, 1, 50% because it's right in the middle, for example, from up or down. Okay, so how we get the power from quantum computing is actually when we combine more than one qubit. Okay, just having one qubit is still probability 1 and 0. Okay, with a classical register, if you combine several bits, you still just get one number that can be stored in the sequence of bits, right? So if we, for example, have 3 bits, we basically can store a number 0 through 8 because we have 8 different combinations for 3 bits. Okay, the quantum computer, you actually have exponential. With 3 qubits, you actually have 2 to the 3 possible combinations because you have probabilities. So instead of just storing one value, you're actually storing all 2 to the 3 at one time in terms of the computation. Okay, and this is where it scales. So it's basically, if you can encode with enough qubits, this is why the push to get more and more qubits in the newer machines. Many computations, if you do brute force search, where you're basically searching for example, a traveling salesman problem, where you want to find the shortest path through cities, the regular computation would basically have to enumerate every single permutation of the city, check it one at a time. The quantum computer basically just encodes all of the n factorial permutations, for example, at once, in a set of, if you have a big enough number of qubits, and then the computation is basically linear in the checking part. See if do you have the smallest. And hopefully, for example, that particular problem, it'll collapse to the optimal answer. Okay, so the running time is much faster. And again, for we'll see some other examples in a moment. But this is where the combination of the superposition of multiple qubits is where we're going to get the power of the quantum computer. Okay, and this slide was stolen from somebody who was actually, there's a branch called quantum artificial intelligence. Because actually some of these machines, you can actually embed neural networks and stuff, so that's, I didn't have time to do my own slide. Okay, so I mentioned, that I'm not going to go into the details, I'm not a physicist or an engineer, but actually the engineers, there's very competitive companies of actually how do you build a qubit. Okay, and there's actually, this slide illustrates 5 different ways. Loops, superconducting loops, trapped ions, silicon dots that you put a quad, and then people are proposing more stable ones. I think this is Microsoft Bell Labs have topological qubits where you have the wires mixed together, and then you have diamonds type properties where you actually build the qubits out of diamonds and so forth. So, and we don't know what is the best, so it's still fighting, just like the early days of digital computers is basically everybody did relays and switches and follow the thing. It's still early days of quantum computing. We actually don't know the building blocks yet. Okay, the D wave uses the superconducting loop in their actual model. That we'll come back. Okay, and you can see this slide. It's probably hard to see, but you can see the success rate. They have error rates that are different values. Okay. This is the Microsoft one is just theoretical at the moment, so they don't have a product that I can implement. So this slide was even outdated. It's 3 years old that I built that. So there's probably more advancements since I have this slide. Okay, so quantum computing is actually a special case of quantum information systems or quantum informatics. So Richard Feynman, the guy that did the original thing, he was more into quantum simulation type things, how to model. And basically, anything that requires more than 20 qubits is not possible to solve with the classical digital computer. So even some of the computers now can be solving more problems than the digital one for that particular area. There is a debate in terms of when will quantum computing be useful for the real world. I think the general consensus may be still 20 years away before the regular supercomputer that people use now with GPUs and everything that's stable. You can actually do some computation better, but it is progressing fast in terms of the products that are coming out. Okay, so quantum cryptography, communication is if you can communicate quantumly over distances and so forth. There's different branches of quantum information. Okay, so this, in the diagram here, is a little bit hard. It's basically the intersection of computer science and quantum physics. A little bit is what we call quantum computing. Actually, we want to solve regular, hard computational problems with the assistance of quantum, or the physicist view. Actually, I should probably throw in engineers too, because actually the engineer actually has to build the machines, right? Not just the theoretician. The theoretician gives the idea why it works and the properties. The computer scientist basically just says, oh, it has this nice property. How can I exploit that in my program to try to solve something? Okay, so one of the initial cracks, RSA, all your banking or whatever, one of the first algorithms was Shor's algorithm. I think it was this paper that he publishes 1997, but I think a couple years before in some conference he actually published the result. So what the thing is, if you're given your security of your system is based on a big number, which is a product of 2 primes. And the question is, if you're going to crack it, want to break into your bank account, the current encryption systems are based on basically solving this problem. Okay, so the paper itself quotes, it's sort of an unfair thing. For example, the standard thing where you have 1,000-bit numbers, okay, probably even bigger than what I've printed here as an example. I just get an example. Look for 2 primes and multiply them together. It's easy to go from multiplication to the number, but given the number, factor it. That's the hard bit. So that's how the encryption works. Okay, so the paper was promoted, is basically the current classical algorithm is exponential. It's mentioned that exponential is some power of the function of n is the number of bits that you're trying to do. Okay, so it's a huge number of years. Okay, the quantum algorithm, Shor's algorithm, in theory is polynomial. Okay, but this is misleading because that assumes the quantum algorithms run at the same speed as the fastest digital. But it's still better. It's still, if we have actually a quantum computer, we don't have one big enough to factor. Okay, as the previous slide I mentioned, we had quantum up to 30 qubits or whatever. Okay, we need basically up to 100 at least before we can do the quantum factoring. I'll come back to this in a minute. I actually should go back to the previous slide and actually mention most quantum algorithms are not using Shor's algorithm as a basis. They're actually using something called Grover's search algorithm. So I mentioned the traveling salesman problem, the Hamilton. There's a quantum algorithm it's actually using as a subroutine. There's actually a Grover's search algorithm. It's a thick width of searching for combinations and then finding the results. So this is actually for applied quantum computing. The search Grover algorithm is more, but where quantum computing became famous was Shor's algorithm. You exhibit an algorithm that you can do quantumly faster than the digital. Okay, so I'm using the words digital, classical, synonymous, the old traditional computers.
But first, Nobel Prize was for Grover's. Nobel Prize was for Grover's.
Okay, yeah, so somebody heard of Grover's algorithm. Okay, so I'm just going to give a synopsis, a very overview of actually the computing process with quantum. So how we actually do the quantum computing, we have all of these qubits. Okay, so you're not expected to read the stuff, it's too small font, but just to explain the general 3 stages. So one is just to get all the states in a random, uniform, all possible combinations of what you're trying to do. So this is activate the spread type phase of your quantum process. And then you want to encode your problem, put biases on which states, in terms of the optimization problem, you have a bias. For example, we do the annealing, you want the optimization curve. If a certain state, we want to penalize bad states and reinforce good states. So this is sort of encode the problem on the machine, put some constraints, entanglements, and so forth on the system. And then basically you have several phases of the algorithm where you want to filter the bad cases out and get the probabilities of the one for your solution to the good phase. And this is what we call unleash the power of the quantum computer. So this is the magic of the machine, supposedly. Okay, so that's the general design. So when I get to at the very end, I'll give a little tutorial of actually using the D-Wave computer. It's basically the encoding will have a specification, we'll map our classical problem to a form that the digital or the quantum computer can execute, and then when we actually run on the quantum computer, it's doing this magic here. We just assume it does what the sales brochure says it does. Okay, but then we can also verify the answer to see if it can't cheat us, because we can verify classically with polynomial or efficient time to see if it actually gives the answer. So that's why people will keep buying these machines if it actually does and solves the problems that they actually want it to solve. Okay, so D-wave computer. So I'm in the second phase of my talk, which I'll speed up in a moment. It's basically the history it's a Canadian country in near Vancouver, British Columbia. The first ones were actually in 2011. Those are, like I mentioned, $10,000 change. You can buy one of those computers. And then all of the big companies don't want to be left behind. So a lot of the big companies, they bought the Lockheed Martin, Google, and so forth, NASA. They bought one of these D-wave computers just to experiment. And so some people suspect Google and others bought it just to take it apart to design their own computer, right? They can invest. They have lots of money just to buy to inspect what's going on. And there was a lot, originally, people were skeptic. It may be a fake machine. It may be like those, people thought it was like those quantum simulators by Hitachi and Fujitsu. They actually pretend, but then you just have a classical computer doing the simulation. Okay, so there have been some papers. I think people are now convinced it does actually do some quantum physics type work. It's not just pretending to be a quantum computer. Okay, I'm neutral. I'm an academic, so I just want to say I have my combinatorial problem. Does it actually solve it? And I'll use it. So the work I've been doing in the lab with Chris Kalude and our students, we've basically, initially we're skeptic, right? But then if we're actually getting results, then we start to curve towards we're liking it. Okay, so that was the history. It's actually, and I have to mention later, comparing qubits are different. So when IBM says they have a 30-bit qubit and D-Wave says it has 2,000 qubits, they're not really comparable. There's like false advertisement going on in some issues. It's like you may have brought graphics cards for your PC. They say number of cores and streaming processors, but originally they were pushing streaming processors are more important than actual cores. But the later models are bumping up, well, we can sell the process with this number of cores. So it's a lot of part of this is marketing and gimmick in terms of the product. Okay, so you have to be buyer beware. Okay, another thing, I mentioned two general models, the circuit gate model of quantum computing and the adiabatic model. The adiabatic is actually not a universal computer, or in the sense it's not trying to solve everything. It's trying to take just one problem and do it well. It's like a special customized hard device. And then the way we run it is we use the standard classical conversion. If you know about NP completeness, maybe if you took my stage 3 algorithms class, you would know that you have polynomial time conversions between any hard problem. That's the way we're actually running the quantum computer. We have our hard problem, we do polynomial time on a regular computer, convert it to its algorithm solver, and then we solve it on the quantum computer. Other theoreticians, the gate model, whatever, they're trying to basically saying, we give you a set of quantum gates. You can build basically like the traditional Turing machine that can solve any computation directly. Okay, so there is slightly different models in terms of what you're selling. Okay, so the one we're doing is not universal. Okay, I'm throwing, I know, terms like Turing, Alan Turing, whatever. He's the guy that did the first stored program computer. And actually the architecture, von Neumann, were basically determined where you store your program and you simulate the execution of the program. Those are the circuit gate model is trying to mimic that. The adiabatic model is more modeling just, we have a black box solver that can solve what we'll see as the Ising or Qubit problem, which I'll specify later. Okay, so in terms of Moore's law, you may have heard of the capacity of IT stuff grows exponential, number of qubits. So from 2004 to 2016, they started with 4 qubits. The one we're actually running on is this one, the D-Wave 2X model, which has about 1,000 qubits. But they did come out with a newer model just recently, which has 2024 qubits, which is and more precision on the values you can store on the qubits and so forth. Okay, so they are making progress. Okay, inside it is basically, here's a rehash, is basically a big dilution refrigerator encased to prevent sound vibrations, and you want to keep it at a cold temperature. And then at the very bottom is actually the computational quantum processor. Okay, and this is our black box solver, is this quantum processor. Okay, and some specs from D-Wave, they tell you it's 175 times colder than interstellar space, is how you run it. They have shielding for vibrations. Okay, so you're not allowed to have radiation outside external. That's what the big casing unit is for. And then the vibrations on the floor, I guess IBM they avoid vibrations on the floor by mounting them out from the ceiling. And the surprising thing, the traditional supercomputers or whatever use lots of power or whatever, energy. Actually, quantum computers are pretty low power consumption for, it's basically you spend the power on a refrigeration, a freezer type mechanism for the computation. So basically you can see from the stack, they get colder and colder as you come down the various layers to the very bottom processor. Okay, so as I mentioned before, the D-Wave uses the Josephson junctions as their implementation of a qubit. Okay, so basically we can view zeros and ones as spins. If you're spinning this way, you view it as one orientation. You're spinning the other way in terms of the flow, the current on the junction. That's how we'll represent the qubit. Okay, so, okay, I'll come back to that. So the actual, I mentioned in terms of the qubits, the mechanism, what we want for a real computer, this is actually connecting qubits. This is sort of the structure. The while says this qubit can be connected to this one. The graph theory construction is sort of this way. They have basically these stars in a big grid. Okay, so notice there's little missing bits here. So this is like Los Alamos's D-Wave system. And what are those missing bits of the original? Well, it's the engineering fabrication. If you have a little speck of dirt, you have faulty qubits or faulty couplers between them. So now it's like the old days when you did buy your LCD monitors, they had dead pixels. You said, "Yo, good deal 20 years ago if you only had 3 dead pixels." Here you buy a quantum computer, you have to live with the fact that you may have some dead qubits and some connections between the qubits that are dead. Okay, so in terms of the programming, you have to realize if you're going to map your problem on the machine, you have to avoid these dead spots or route around the dead spots with your qubit layout. Okay, so it's basically, we have a bunch of those. This is the current D-Wave architecture, but they're actually switching to a slightly different one, which I'll mention in a minute. Okay, so I mentioned comparing the 30 qubits of the IBM system versus this one. The ideal best quantum computer would have every qubit has a connection with everybody else. But in the engineering facility, you can't actually put wires or connections between, you can't entangle every single qubit. So that's why D-Wave can have more qubits, because they spread them out into sort of, but then your programming, you have to realize that you can connect only a certain subset of the qubits together. You can only entangle a few things. Okay, so here's what I mentioned. The current one is the chimera graph. So I don't know, picture, I just stole it from D-Wave website. It looks like a regular digital computer or circuit, but that's actually the logic. Okay, so the newer prototypes, they call the Pegasus. The Chimera is the current ones up to the D-Wave 20. It's basically 16 by 16. That's what the 16 of these little star things is what the 16 is. The Pegasus is a different prototype. It has just the next generation of designing architecture. And it looks like this. The good thing is the Pegasus will have more connections to other qubits, so it's more dense. So you actually can hopefully do, when it's a prototype now, we don't have a real one. It'll come out with more qubits. They propose a P16 with 5,000 qubits. The thing is, each qubit is connected with 15 others. The current Chimera architecture, you can only connect with 6 others when you're doing your entanglement, whatever coding. Okay, so the actual programming, okay, so this is your computer scientist now. Well, you don't have to care about hardware. It's basically, this is their promotion. The purple stuff is, they develop a software library that you can use that eventually calls the D-Wave quantum machine instruction down here. So what we program is the regular programming language. We specify it. I mentioned that you transform a regular computational problem into a D-Wave model, and then you execute it on the D-Wave. They're proposing, that's what this gray stuff, other things. They know AI is, and machine learning is a popular topic. So they're currently building interfaces that'll take your AI or machine learning project, go through the virtual qubit thing here is a way to break up your problem into small pieces if it's too big to fit on a current machine, and then combine the results. Okay. What we've been doing in our local research group is basically directly to the software application programmer interface. That's what the SAP. It's like other libraries. You have an interface where you call functions. Okay. Okay, so just to confuse you, this is the math part you can ignore. So the quantum machine instruction, the black box solver, actually solves what we call the Ising optimization problem. Okay, so that's the only thing it can solve. And this problem is NP hard, which means basically nobody knows a polynomial efficient algorithm to solve this, but we can map other hard problems to this problem. It's basically we program it by specifying strengths of the individual qubits, which we call the H vector, and then this corresponding J matrix is like the couplers in terms of the entanglement between the qubits. Okay, so I'm not going to delay it. But notice it's based on the physics view of two states, or -1 and +1. Okay, later we'll mention the computer science fusion where we actually go back to logic with Boolean true, false, or 0, 1. Okay, but the processor itself actually does this Ising physics problem. Okay, I want to briefly mention the other thing about quantum annealing. So if we're solving an optimization problem, for the one we just showed, for example, is an optimization problem, right? With a min of certain, min over all possible combinations of this spin vector, we want to, that's what the thing will solve. Okay, so that's basically, if you can view it in the two-dimensional case, it's actually n-dimensionals, but the picture says we want to find this minimum point here or here. There may be more than one optimal value. The regular search space that you explore, if you have a digital computer, you basically go and you get stuck in a tunnel and have to leave. Okay, the fluctuations of the quantum system, supposedly the states will actually allow you to tunnel through the landscape and hopefully get to the minimum. Okay. So that's one of the features they're promoting for quantum annealing. So annealing comes from the process, the word comes from the mechanical, you have heating, cooling, and you want to get to a stable state. Okay, so I want to know, I'm starting to lead up to the little tutorial. I have a little toy problem just to show you the inputs and outputs. Okay, so what we need to do is formulate our problem. So different problems, we need to specify it, convert it to this Ising optimization problem, or equivalent later, we'll see the qubit representative. We do pre-processing. We want to do all the easy things first with the classical computer. The next thing, which is a little bit hard and confusing, which takes probably most of the time, is actually, once we get the problem specified as the Ising qubit, we now want to assign the variables, the spin variables, to actual physical qubits on the machine. Okay, so usually the structure of your mathematical model doesn't map directly because it's not a complete connected qubit construction. So we actually have to do an embedding problem. Okay, okay, then we load the values on the system. We call it's a probabilistic thing with many runs. We call the black box annealing thing. And then the final thing, we collapse the state to the digital form. So this is, again, Schrodinger's cat type view. Everything's flux triangle combinations. We collapse to the set. And then we get some results, and then we do classical post-process analyze the results. If it's good, we stop. Otherwise, we may need to run it a few more times on the device, our current model. If it's still bad, we may have a very bad formulation of an Ising or qubit that's solving a problem. Then we go back to step one. So that's the design flow of using a D-Wave to solve computational problems in a general form. Okay, so what is the embedding problem? Okay, so this is a minor embedding. if you have a structural Ising or qubit problem that this, basically you look at the non-zero entries of the matrix, that matrix. If it's non-zero, you have a connection. You have an interaction between a couple of the qubits. Okay, so suppose we have this type of interaction system, there's something called a minor order where you want to embed on, say, a fictitious hardware architecture, a grid. We want to basically take some of the qubits, split them apart, and entangle them so they have the same state. So this A qubit is now replaced with two, so this is the logical structure, two physical A qubits, and so forth. So this is now a subgraph, can be embedded directly on this fictitious hardware. So you can view this would actually be the Chimera Pegasus architecture, but I'm just illustrating what we have to do is embed, and this is called the minor embedding problem. Okay, and this is a hard problem. Surprisingly, when I was a PhD student, knowing nothing about quantum computing or anything, I was actually working in the structural graph theory type problem. So luckily, I knew a little bit. I was trying to classify graph families by basically forbidden minors. And this is the embedding problem. So I had a little bit of a head start using quantum computing because I have an intuition of how to embed logical structures into the physical hardware. Okay, so that's one of the things. And notice I had the pink here, and there's actually more than one possible embedding. So for this particular example, I put C, I entangled it into 3 qubits, but the problem is it's actually probably better to entangle F with somebody else, so we have something called the max chain, which is if you're doing an embedding, the maximum number of qubits, a logical qubit gets mapped to a physical qubit, and we want to minimize that for accuracy on the actual machines. Okay, so for example, I have a couple more just examples. So this particular, if that's your logical thing, this is your hardware. You have to replace these yellow with these 3 yellow. So we would actually run on the machine in this configuration, and then the post-processing, you get the answers, we have to map it back to the original input structure. Okay, so if we had lots of problems, if we have an embeddings of the completely connected architecture, then we don't have to worry about embeddings. We can just say if we know how to embed the completely connected structure, for example, in here, but they're using a lot of physical qubits, this pretending, we can then, if we have another structure that's, for example, this graph with 3 or 4 missing edges, we can still use the same embedding. Okay, so we don't have to do the embedding process. So a lot of people are interested in embedding the complete graph, what's the largest. And it turns out for the Chimera graph, the D-wave architecture, you have n qubits, you can do square root of n complete graph, assuming we don't have faulty qubits or couplers violating the paths or the connections between the individual qubits on the system. Okay, so here's another view of we can index the Chimera. It's just, you can do a mathematical. You want to give names for every single qubit, so when you're mapping. So this 4x4 is the same thing as the star. The star was 4 horizontal and 4 vertical connected, but oftentimes you see the representation of the Chimera graph in that format. Okay, I have a couple other slides. So oftentimes you have a structure that's complete bipartite, a set of vertices that are isolated, connecting to another set. So there are some rules of mapping complete bipartite graphs to the Chimera graphs. So you don't have to do the embedding problem from brute force area or from. Okay, so just a summary of embeddings. So complete graph we can do up to 17. Completely connected, no, 64 on the Chimera 16. I guess the 12 is the current one, which is about 40. Okay, so the problems are in the Pegasus, P6, and there are more connections, so you actually can get better graphs. Okay, so one thing that may be interesting, there's a standard brute force integer multiplication circuit or structural thing. So this is the goal. Are we going to solve RSA in factoring? So currently the machines can only do 16 bits, which is not so good in terms of the actual quantum market. So RSA is still safe for a long time, but so they say at least 20 years before there'll be any scare of solving encryption. And the blue is the max chain, so that's a single logical qubit mapped to several hardware qubits. That's what I call the max chains. And our experimental work actually with existing chimera graph, the D-wave 2x. If you can keep that under 8, you actually get accurate results. If you start exceeding 8, the fluctuations of the connections deteriorate the reliability of your answers from the machine. Okay, so this is just a recap. We have to do a problem, we map to Ising, embed, run several times, and then post-process. Okay, so I have a 5-minute tutorial with a simple example. So the Ising problem is easily transformed. Instead of -1, +1 for the variables, here you're trying to solve the standard computer science false, 0, 1 is true. So we can think in terms of binary optimization with true false. And it's basically the same minimization of a quadratic. You have a matrix. So they're equivalent. And one thing to notice, the linear terms disappear here because in terms of Boolean or binary, x squared equals x. If x is 0, 1, you square it, it's still 0, 1, right? Okay, so that's why it's a little bit simpler than the previous Ising model formulation. Okay, so the example I'm going to illustrate is maximum independent set. It's a toy problem, NP hard. This problem is, for example, if you're Starbucks and you have cities or intersections, you want to put a Starbucks, but you don't want to have a Starbucks competing with a neighboring Starbucks. So you want to find positions in your city that are independent. No neighbor that's the same. So, for example, this cube, you can put 4 independently non-conflicting things. And this is the maximum independent set problem. Okay. So here's 6 different independent sets. The good ones are the larger number of red vertices. Okay. Luckily for our Kubo formulation for this is basically an embedding. This is such a nice problem that it actually don't need embeddings. Because the actual structural, the Kubo structural is actually the same as the graph. Okay, so you can view the graph different than the Kubo interaction graph, which is the thing that we embed on the hardware. So here we can just basically, we want to minimize a formula. Okay, so the D-wave does the minimization. So basically if we select a location, we want to assign -1 for selecting it. If we actually select 2 locations that actually have an edge together, this is where we put a penalty of something greater than 2. So it cancels out selecting the 2 places for your Starbucks because you have an edge, you get a +2. So we can fill the matrix with the diagonal entries. With -1 means we get the low value if we actually get to put a Starbucks on that node of the graph. But if we actually pick 2 nodes that are adjacent, connected by, we actually get a penalty. So the system wants to find the combination of which nodes to do. That's the problem that the D-wave is solving. Okay, so the API I mentioned, the program, I program in Python, calling the library. So there's a bunch of libraries you call, D-wave, SAPI, whatever. So I'm going to illustrate with this graph, running it on the D-wave machine and see what we expect. So looking at this graph, the independent set, you can see there's, if we take 6, 4, and 5, those are independent, but you can't have more than 3. Or you also can do 2, 0, 1. Okay. The acute audience member will notice, why am I missing 3? Okay, because these labels are actually, we want to actually, in the embedding problem, if you go back, I don't know if you can see this, this is the labels of the connections on the actual hardware. So I actually wanted to embed neighboring vertices of the graph such that there actually is an edge. So this is 0, 1, 2, 3, 4, 5, 6, 7. So I'm using this top 6 vertices of actual D-wave, so I don't have to do the embedding. So that's why I commented out in Python. I don't actually need to do the embedding because I actually know my structure and I know where to embed the vertices such that there actually is a qubit coupler on the hardware. Okay, so the API also has this thing, we can specify the Kubo matrix Q. The API has a mechanism which is very fast to transfer Kubo to the Ising, which is actually run on the hardware. Okay, so we get the H and J for the Ising formulation of the problem. Okay, the next, so there's a 2-page program. I call over the cloud, I put into my credentials, my password, which solver machine I want to use. I connect to the machine with my URL token. Okay, this I'm just printing the property so you can see this is not needed. But then I run the machine by just call their black box solver. So it's not hard for a programmer. The hard part is getting the Ising or Kubo formulation. Okay, actually using the machine was also gimmicky because there's several parameters. The annealing time, the thermalization time, you have to specify all of that. The number of iteration, number of reads or so forth, you specify. Spin reversals, you want to say for those qubit couplings, you want to orient spin up or spin down, depending on one another. The spin reversals, to get the stability, you want to try different combinations of spins in terms of how you view a qubit. Okay, so here is the output I run. The first page, I'm just echoing, printing the Kubo, printing the Ising, and then a bunch of properties, which basically just list the options you can do. That's not really, you usually don't print the properties. The next slide, I've ran it 2 times, and you can see the solutions it gives you. It runs, it's probabilistic. It actually found, out of the 100 runs I did, both optimal answers. It didn't give any wrong answers. So the first run I had 42 instances. If you look here, -1 means not using the vertex. 1 means you're actually using it in terms of your independent set. And the other one was, so this is those 3. And notice qubit 3 is not used, so that it's -1. So I ran it again, similar. You get both evenly probability answers, roughly half time. Okay. When I ran it on the older machine, I actually got some other solutions that were not optimal, but you can at least get your answer and you can check if it's a valid answer. Okay, so that's my tutorial on actually what you get from the machine. You actually get many probabilistic answers, and then you can post-process and check if you got the right answers. Okay, so that was basically what I wanted to do, and I just have some references of stuff we've been doing at our lab recently in the last couple of years. Thank you.